The second part of 7.3 is about the translation on the t-axis. This part we are going to use the unit step function and the Laplace transform to solve the differential equation problems. In engineering, very often we encounter the functions that either on or off. For examples, the mass spring system. And we have the differential equations as m times x double prime plus beta times x prime plus k times x equals f of t. Or the circuit problem, that's the E of t or the voltage resources equals the L times the I prime plus the R times I plus the 1 over C multiplied by Q. The external force for the spring problem as the F of t or the E of t as the voltage source of the system that can be on or off. For example, if we can find a function that set it to be off or to be the value 0 up to the certain period of the time t equals a, and then make it on or the value of the function will be 1 after that time, that kind of special function is called the unit step function. And we can be able to solve this kind of problems. You might be familiar with the function f of t, which defined to be 0 for t is less than 0, defined to be 1 for t is greater than or equal to 0, and the graph of this piecewise defined function form is the function will be 0 for the value t is less than 0, and the function value will be 1 for t is greater than or equal to 0. And this is the original step function graph. Now we are going to look at the definition of the unit step function that has the translation on the t-axis over to the t-axis by a units. Use the notation script u or u of t minus a, which is defined to be 0 for t is greater than or equal to 0 but less than a, and defined to be 1 for t greater than or equal to a. And the graph of this unit step function is the translation of the original unit step function by translating to the right side by a unit. So the value of the function between 0 and a, not including a, will be 0, and the function value from t equals a on will be 1. Now we can represent the function f of t that's defined for t greater than or equal to 0 in a piecewise defined function form as the f of t multiplied by the unit step function or defined to be 0 for t greater than or equal to 0 but less than a, and defined to be f of t for t greater than or equal to a. Another type of the piecewise defined function form as the as is defined to be g of t for t greater than or equal to 0 but less than a, and defined to be 0 for t greater than or equal to a. In the unit step function form, it will be g of t minus g of t times unit step function t minus a. I can show you real quick how to derive this form as the function in the form of the gt defined for the first part from 0 to t and less than a, and then 0 here for t greater than or equal to a, is the same as you write it as the g of t minus 0, and for the 0 is the same as g of t minus g of t. And then we can rewrite this as the difference of the gt and the piecewise defined function that defined to be 0 for the first part and gt for the second part. Then we can see this in the unit step function form as the gt minus gt times the unit step function t minus a. Now I'm going to name the first box with the star and the second one with the 2 stars. In this way, we can use the unit step function to write the piecewise defined function in the compact form. In the case that both piecewise defined functions here are not 0, or in the term of the function g and the function f, we see this as the sum of the two piecewise defined functions as the first one is the gt and then 0, plus the second one as a 0 and the f of t. So the first piecewise defined function can be written in the unit step function as the gt minus gt times unit step function t minus a. And then the second piecewise defined function in the unit step function form will be the f of t times unit step function t minus a, or the use of the 2 stars box and the 1 star box. These examples, we are going to express the following functions in terms of unit step functions and then graph. The first one, f of t is defined to be 0 for t greater than or equal to 0 but less than 5, and defined to be 3 for t greater than or equal to 5. So the point of translation a is 5. Now we can write the piecewise defined function as 3 multiplied to the piecewise defined function that's 0 for t greater than or equal to 0, less than 5, and 1 for t greater than or equal to 5. Then we can see this as 3 multiplied by the unit step function t minus 5. Now we're going to sketch the graph. The point of translation is at 5. Between 0 and 5, including 0, the function value is 0. And then for t greater than or equal to 5, the function value will be 3. In this example, the g of t is defined to be 20t for t greater than or equal to 0, less than 5, and defined to be 0 for t greater than or equal to 5. The point of translation occurs at a equals 5. The piecewise defined function can be treated as 20t minus 0 for the first one and 20t minus 20t for the second one. And then we can see this as the function 20t minus the piecewise defined function that defined to be 0 for t greater than or equal to 0, less than 5, and defined to be 20t for t greater than or equal to 5. Now, the gt can be rewritten in the unit step function as the gt, which is 20t, 20t minus 20t times the unit step function t minus 5. Next, we're going to sketch the graph. For this case, as the point of translation occurs at a equals 5, between 0 and 5, it goes with the function 20t, or the line with the slope 20, and the intercept is at 0, 0. So at 5, the function value will be 100, but we omit that point. And then for t greater than or equal to 5, the function value will become 0. This example, the function ht is defined to be 20t for t greater than or equal to 0 but less than 5, and defined to be 3 for t is greater than or equal to 5. We can write this piecewise defined function as a sum of two piecewise defined functions. The first one defined to be 20 for t greater than or equal to 0 but less than 5, and defined to be 0 for t greater than or equal to 5, added by another piecewise defined function which defined to be 0 for t greater than or equal to 0, less than 5, and defined to be 3 for t is greater than or equal to 5. As you see, the second one from example 1 and the first one from example 2. In this way, we can write the first piecewise defined function as 20t minus 20t multiplied by the unit step function t minus 5, where 5 is the point of the translation, and then added by the unit step function of the second piecewise defined function as 3 multiplied by the unit step function t minus 5. And then we're going to sketch the graph of this function ht. between 0 and 5, including 0, it goes with the graph of the function 20t, or the line with the slope 20. And then for t greater than or equal to 5, it goes with the function value 3. So now we get the graph of the function ht.